All right, now the one thing I forgot, our first problem, we took this function, and by using the second derivative, we determined that where it was concave up and down and the points of inflection, I forgot I'd actually made an actual graph of this function. So let's see if the graph of the function actually matches up with what we found out. And here I've already sort of marked it up. You can see here this graph is concave up, so the second derivative is positive, and we said concave up from negative infinity until 0. 0 is right here, and we said we have a point of inflection at 0, -9. That looks about right, because you can see it's concave up, and then it switches to concave down. And we said concave down goes from when x is 0 to x is 2. So this is the concave down region where that second derivative was negative. And we said we had another inflection point when x is 2, and the actual point was 2, -5, which matches up. So here's our second inflection point, and then all of a sudden we go back to a concave up region. So two regions of concave up, one region of concave down, and these inflection points. So the second derivative went positive, second derivative is 0 to point of inflection, second derivative becomes negative, second derivative is back to 0 at this point of inflection, and then positive. So it looks like mathematically matches up with the actual graph. Let's do another problem from the homework. This is problem 8. Now instead of f of x, they do f of s, so now our variable is going to be s, just to sort of change things up on you. Now, because I have these parentheses squared, I am from the start going to go and multiply this out, because when I start taking derivatives, it's probably going to be a little bit easier if I get rid of the parentheses. Sometimes you can't get rid of the parentheses, and you could do the product rule here, but I'm going to go ahead and just multiply these out because I think it's going to make it a little bit easier. So when I FOIL this, this is s plus 3 times s plus 3, right? So you get s squared plus 6x plus 9. And when I multiply them out again, so this now is my function without any parentheses. So the first derivative is going to be 3s squared plus 12s plus 9. But what I really want for this problem is my second derivative, so I take the derivative again, 6s plus 12. And now, since I know the second derivative, I can set it equal to 0 and solve this equation and find the points of inflection. This is a pretty simple equation. If I factor out a 6, so there it is. Looks like I have one point of inflection when s is -2. So now, since I know this point of inflection, I can now go figure out where my function is concave up or concave down. So here's my chart. One point of inflection, so therefore I have two regions. Now I go into each region, and I'm going to go look in region 1 and choose a value of s between -infinity and -2, and I'm going to plug it into the second derivative and see if it's positive or negative. So this just choose -3. So the second derivative when s is -3. Here's the second derivative. So I plug in -3 for s. 6 times -3 plus 12. This is -18. -6. Region 1 is a negative region. Negative second derivative means concave down, right? A negative person frowns, concave down. For region 2, I choose a value between -2 and infinity. How about 0, right? 0's in here. 0 is always nice and easy. So 6 times 0 plus 12. Region 2 is a positive region. Positive person smiles. It's concave up. So now I have pretty much everything I need. Let's just go ahead and start listing things. So concave up is when S, the interval -2 to infinity. Concave down is when S, concave down is the first region, -infinity to -2. Points of inflection, I have one. Now once again, they ask for the coordinate. So the point of inflection, -2. Now once again, to determine, in a sense, the value of the function, you can think of it as like the y, I go way back to the original function. Let's go way back up here. It'll be easier. If I plug in a -2 for s here, -2 plus 3 leaves 1 squared times -2. It looks like, if I did the math correct, my point of inflection is -2, -2. Now once again, I took the time, I took this function and actually created a graph. And let's see if what I've said down here matches up with the graph. So let me show you the graph, and then I'll read to you what we determined. So here's this graph. And we said, if we start here, concave down looks like -infinity, and we said concave down -infinity to -2. That looks about right, because here it's concave down and it's going to switch to concave up. So we're saying it happened right here, and we're saying the value of the function is also -2, which I think is correct. So that looks like that's a point of inflection. So once again, second derivative, it's negative, concave down. Second derivative is 0 at the point of inflection. Now the second derivative becomes positive, concave up. And you know what? It's concave up the rest of the graph. So there was only one point of inflection. There's only 2 regions on this graph. So it looks like what we did mathematically was correct. Okay, one last problem. Now this is a new homework section, but a different, I'm going to do number 16. And here are the instructions. Let me read them out of the book, because you'll be doing some of these also. Determine where the given function is increasing and decreasing. So that increasing and decreasing, we use the first derivative to determine increasing and decreasing. And then it says, and where the graph is concave up and concave down. Find the relative extrema, which means inflection. Relative extrema means maxes and mins. And then it says find the inflection points. And then they say make a sketch. So here we're doing the whole ball of wax. We're going to use the first derivative to find where the function increases, decreases, find the maxes or the mins or the neithers. Then we're going to go to the second derivative and find the points of inflection, and then find out where the function is concave up or concave down. So I referred to this earlier, so here's the whole ball of wax. And I'm going to actually work out problem 16. So here's the function, x cubed minus 3x squared plus 3x plus 1. So now I'm going to take the first derivative, pretty straightforward, 3x squared minus 6x plus 3. And now I'm going to stop, and I'm going to take a deep dive into the first derivative and see what it tells me. So once again, now, if I set the first derivative equal to 0 and solve it, these are going to give me my critical points. And they're probably going to be a max or a min, maybe a neither. So to solve this equation, I'm going to factor out a 3. And once again, I can sort of get rid of the 3, divide both sides by 3, it sort of goes away. So really it's a problem of this trinomial, which actually factors into x minus 1 times x minus 1, or it's pretty common, we could have just written that as x minus 1 squared. So when you solve this, x equals 1. So we have one critical point. It's probably a max or a min. I don't know. It could be a neither. I don't know. All I know is one critical point, and I want to find out on either side of this critical point whether my function is increasing or decreasing. So the way I do that is I sort of chart out the first derivative. So here's 1. Turns out it breaks it up into 2 regions. So I go into each region, choose a value of x. I'll choose 0. 0 is in region 1. And I'm going to go back and plug in 0 for x and see what my first derivative equals. So the first derivative with x equals 0 is going to be 3 times 0 squared minus 6 times 0 plus 3. So this is 0, 0, it's 3. First derivative, positive means first derivative, the function's increasing. And that whole first derivative, it's increasing, it's going up. Positive first derivative. Region 2, something greater than 1, I'll choose to set x equal to 2. So I go plug in 2 into my first derivative, 3 times 2 squared minus 6 times 2 plus 3. So this is 4 times 3 is 12 minus 12 plus 3. Looks like region 2, the first derivative is positive, which means it's increasing. So what happens when you have a region where it's increasing, and then you have a critical point, and then it keeps increasing? Well, that occurs when you have like a neither, right? Increasing. I know at this critical point, the function has to someplace be sort of horizontal for the first derivative to be 0. So first derivative positive, somewhere in here, it's 0, and then it's positive again. It looks like when x is equal to 1, we have a neither, right? We call this a neither. So therefore, I now know this function's increasing from negative infinity to 1, and then also from 1 to infinity. There's only one place here when x is 1 where it's not increasing. It levels off, but then it starts going up again. So there's 2 regions where the function increases. So there's my critical point. There's where it's increasing, and there's no place where the function is decreasing. Now, let's go and take the second derivative and take a deep dive into that, and it's going to tell us any points of inflection and also where it's concave up or concave down. So let's just start out. Let me write down here what the first derivative is. So now I want to take the second derivative, 6x minus 6. To find the points of inflection, I take the second derivative, I set it equal to 0, and I solve this equation. hopefully it's pretty clear that x equals 1 is a point of inflection. It's interesting. Sorry. If you look, and this happens sometimes, up here, critical point was x equals 1, which is neither. Down here, point of inflection is x equals 1, the same point. So we'll see how this looks eventually when we try and graph it. So now that we have the point of inflection, we can now go determine where the function is concave up and concave down. And for that, we do our chart. I mark my point of inflection, breaks it up into 2 regions. I'm going to go into each region, and I want to now see what is the second derivative. Is it positive or negative? So for region 1, I'll find the second derivative when x is 0. So here's my second derivative, 6x minus 6. Hopefully it's pretty clear. If you plug in 0, you get negative 6. So this is a negative region. What does a negative second derivative mean? Concave down. Region 2, I need to choose a value of x between 1 and infinity. Let's choose 2. So if I plug 2 into my second derivative, 6 times 2 minus 6, 12 minus 6 is 6. Obviously positive. Positive second derivative means concave up. So they say to sketch the graph. So this is going to be pretty rough, but I know all this stuff occurs. I have both a neither and a point of inflection. Let's figure out for the graph when x is 1 what the function is. So that means let's go back to our original way up here. Let's plug in 1 into here. Let's see what this function equals. So when I plot my point, it can be pretty accurate. When I stick in a 1 here, 1 cubed is 1. 1 squared is 1. So 1 minus 3 plus 3 plus 1. Looks like it's 2. So actually, a point on my graph is 1, 2. So this is both a neither and my point of inflection. So that means graph is increasing. Remember, increasing until you get to 1, a neither and increasing. Let's just sort of graph that. So we could say maybe it's something like this. Increasing, it levels off, and then it continues to increase. Now let's see for the concavity, does that make sense? Concavity says you know what, actually, oh, here it is. I didn't write it down. Concave up, x is 1 to infinity. Concave down, x negative infinity to 1. Is that what we have here? Negative infinity to 1, concave down, 1 to infinity, concave up. So my guess is the graph looks a little bit like this. And once again, because I was able to, I went ahead and created the graph electronically. So here is x equals 1, which is 2. So we're saying this is a neither. It's where the first derivative is 0. We have increasing, increasing. So 2 regions where the function's increasing. So in terms of the first derivative, it's positive here. It's 0 here, positive here. Now the second derivative, This is concave down. Second derivative is negative. Second derivative becomes 0 here because this is a point of inflection. And then second derivative becomes positive here. So the first derivative, it's positive on either side of this point. Second derivative changes from negative to positive. All right. Now, there's one last thing we can do that's very helpful with second derivatives. So we've covered second derivatives, the main stuff, but now I want to show you sometimes the second derivative allows us to take a shortcut for a certain kind of problem. Now normally, in the past, if you've ever given a function and we were asked to find the maxes and the mins, that's pretty common. And to do that, right, you take the first derivative set equal to 0 and you solve this. And when you solve this, you get the critical points, right? But then we normally had to do the chart. We had to look on either side of their critical point and see whether the first derivative is positive or negative. All right, we did that. We can do it. It's not that bad. But there's a shortcut. Instead of having to do this chart, what I'm going to show you in a minute is once you find your critical points, if it's easier, and a lot of times it is, you can go and look at the second derivative. And the second derivative, you know your critical points. You actually plug each critical point into the second derivative, and it will tell you whether that critical point's a max or a min. So if you want to skip having to do the chart, which is sometimes of a pain, now the second derivative says basically you don't have to chart it. Once you know your critical points, if you go find your second derivative, then you can right away find out whether those critical points are maxes or mins. So let's go ahead and do a problem, and I think you'll see once we do it how it sort of makes sense. Well, let me take a minute and show you why this makes sense. Because what you've done, when you find the critical point, normally they're maxes or mins, but you don't know what it is. So if, say, this is your function, when you find a critical point, all you've done is you've found these values of x. You don't have a graph. You don't really know what these points are, because all you have is an equation. But if I look at this, for a max is always part of what? A max is always part of concave down. A min is always going to be part of a concave up. It has to be. A maximum is always part of a concave down. A minimum is always part of a concave up. You know what that means? Also at a maximum, second derivative, anytime you have concave down, it's negative. Anytime you have a minimum, which is part of a concave up, for concave up, we know the second derivative is always positive. So how does that play itself out? Let me just write this, then we'll do an example. So you're given the function, solve the first derivative equal to 0, and that gives you your critical points. Then find second derivative, plug each critical point into second derivative. Now, second derivative is positive, that means you have a minimum, right? Positive second derivative is concave up, you've got to have a minimum. If second derivative is negative, then you know that critical point is a maximum, right? Because a negative second derivative is concave down, which means you've got a maximum. So let me do a problem, and then hopefully this will even become more clear. Let me start with a new sheet of paper so I don't run out of room. I'm going to do problem 30 from the book. So here's what problem 30, the instructions say, use the second derivative test to find the relative maximum and minimum of the given function. So it's saying use the second derivative test, use the second derivative to find out whether these critical points are a max or a min. So problem 30, here's the function x plus 1 over x. I'm actually going to rewrite this so I can take my derivative. 1 over x, I switch to x to the minus 1. So now I'm going to first find my critical points. To do that, I'm going to take the first derivative, which is 1. All right, for this one, negative 1 comes out front, and you subtract 1 from your exponent, right? So this ends up being 1 minus 1 over x squared. A little different. Matter of fact, just for fun, I'm going to combine these into one fraction. I need a common denominator. I can rewrite 1 as x squared over x squared minus 1 over x squared. So now I can write x squared minus 1 over x squared. And just for fun, you'll see later on this makes it easiest. This is a difference of squares. I just did this because I like algebra, and maybe in the long run it'll make this a little easier. So now, to find the critical points, I'm taking my first derivative, setting it equal to 0. Now hopefully I've mentioned it before. Whenever you have a fraction equal to 0, the solution is you simply take the numerator and you set it equal to 0. There are no solutions that come from the denominator. It's almost like we can ignore the denominator when we're trying to solve a fraction equal to 0. So you take the numerator, set it equal to 0, and in this case, we have two solutions. So those are our critical points. At this point, I don't know if those are maxes or mins or neithers. Now, previously, at this point, I would do a chart and mark them and break into regions, and that's a lot of work. However, now I have this thing where I can use the second derivative test. So let me write the first derivative, and I'm going to do it in the easiest form possible. I'm going to go back at this point and say this was my first derivative before I did all the factoring, because this will be easier to take the second derivative. So now I take the second derivative. In other words, I don't want you to be confused. This was my original first derivative, and I simplified it. I did all this work because I had to solve it. But now that I'm going to take the second derivative, I want to go back to what I think is the easiest form of the first derivative in order to take the second derivative. I don't want to have to take the second derivative of this. That's a mess. This is not too bad, right? So if this is the first derivative, the second derivative, this is 0. You have the minus, right? Minus 2 comes down. Turns out it's 2x to the minus 3, which I can write as 2 over x cubed. This is the second derivative. So what the second derivative test says, okay, these are the critical points. I'm trying to find out whether they're max or mins. What I can do is I can take each of these points, plug it into the second derivative, and then that will be able to tell me if I have a max or a min. Why is that? Once again, if the second derivative ends up being a positive number, it looks like this. You've got a min. If the second derivative is a negative number, you've got a max. So let's do, for my first critical point, x is -1. I take that, I plug it into my second derivative. 2 over -1 cubed. -1 cubed is -1. This is -2. What does a negative second derivative mean? It means concave down. What does a concave down mean? That point is going to be a maximum. Has to be. Let's look at my second critical point. For x is 1, plug it in to my second derivative. 2 over 1 cubed, which is 2. What does a positive second derivative mean? It means concave up. What does a concave up have to have? It has to have a minimum. So, we've got a max at x equals -1 and a minimum at x equals 1. So that's called using the second derivative test to find out whether you have a max or a min. All right, that finishes this section, and we will continue on.